In this lesson, we are going to convert the 32-bit float sample values into unsigned 16-bit values before we store them into the audio buffer. I mentioned we would do this at the end of a previous lesson, but held off on the details until now because it can be a little confusing how and why we do this. Looking at this diagram again, it shows the float values on the left and the signed 16-bit values on the right. Signed 16-bit values are half positive and half negative values. Unsigned 16-bit values are all positive values. Both signed and unsigned 16-bit values have a maximum of 65,536 values total, including 0. The reason why we have to convert the values is because the how functions that operate the I2S interface will be expecting unsigned 16-bit values from the buffer, and the digital analog converter requires a 16-bit value for 16-bit mode. But notice I did not say the digital analog converter requires a signed or unsigned 16-bit value. It won't care because over the serial port it will only see one bit at a time and there won't be any typecasting in the raw data. If we tried to save signed 16-bit values to the buffer, the compiler would give us errors because there would be conflicts between the unsigned values the how functions were expecting and the signed values we tried to pass to them. Once the digital analog converter gets the 16-bit values transmitted to it, it will likely treat them as signed values and produce negative voltages for negative signed values, along with the usual positive voltages for positive values. Let's go ahead and take a look at the code and see an example of how these conversions are done. Previously, we processed y equals wave compute f0. And it returned a sample value that we stored in y. We can see the next step. YL equals YR equals Y. Here we are simply making copies of Y to YL and YR. Moving on, we come to YL equals YL greater than 1.0 F question mark 1.0 F colon YL. And YL equals YL less than negative 1 question mark negative 1 colon YL. What this simply does is if YL is greater than 1, then it will equal 1. And if it's less than negative 1, then it will equal negative 1. And the same thing for YR. So basically what we're doing is we are limiting the sample to be a positive 1 or a negative 1. Bad things could happen if we exceed these limits. Finally, we come down to the code that does the conversion. Value L equals unsigned integer 16, 32,767.0 F times YL. And we have the same thing for value R. This is how we get values of negative 1 through positive 1 to become a unsigned integer 16 type value. I will use a couple calculators here to process the next examples. One calculator that's built into Windows 10 will let me do decimal values. The other calculator is a nice little programmer's calculator that will show hex, binary, and integer values in various combinations. Now the way our code works is first we multiply our value YL times 32,767. Now the reason why we're doing this is because we're going to end up with a signed integer value that is either going to be a negative 32,767 or a positive 32,767. Because remember, our maximum either way will be a 1 or a negative 1 for YL. So for an example, let's say YL equals 0.8. And we'll multiply that by 32,767. And we come up with 26,213. Now we still have a float value here, this 26,213.6 is not an integer, so we have to drop off the 0.6. Now let's go over to the other calculator, and we're going to choose 16-bit values. We're going to say signed, enter a decimal value, and we're going to enter the value 26213. And again, we have this casted as a signed value. So we end up with a hex value of 6665 and a binary number shown here. And notice the binary number here is 16 bits long. Now, if we had a sample value of negative 0.8 and multiply that by 32,767, we will end up with a negative 26,213. So going back to our other calculator, we can quickly change this into a negative number by clicking this positive negative button. Now see what happened? The hex value changed, and so did the binary value. We can go back to the positive value and see it changes back. So a positive value is hex 6665 and this binary number, but if we change the integer here to a negative, then the binary number changes and the hex number changes to 999B. Now let's leave this as a negative value and change it from a typecast of signed to unsigned. So click on unsigned, and you will see the integer value has changed to 39,323, but the hexadecimal number has not changed and the binary number has not changed. We can go back again and see the difference between the two. What I wanted you to see here is, even though we started out as a signed 16-bit negative value, when we change it to a unsigned type, the binary value did not change. The binary value is all the digital analog converter will see, and it will do with it as it sees fit. And assuming the digital analog converter will treat the 16 bits as signed integer type, it will have a range from negative 32,767 to 0 to positive 32,767. It will convert these values into voltages that range from around negative 2.7 volts to 0 on up to positive 2.7 volts. Getting back to our code, after we do a conversion, we are back again to look at this. Out P++ equals value left, and out P++ equals value right. Here we finally store our 16-bit values into the audio buffer. We increment the value of the address inside our pointer, out P, each time we store a value. That way the next value we store will sequentially be the next memory address in the audio buffer. After storing our values, we go back to the beginning of the for loop and check to see if we continue or end the loop. If POS is greater than length, the for loop ends, freeing up the CPU to do other things while the DMA continues to stream out data. Be sure to go over these concepts a few times and fully understand them, especially the areas where we have gone through make sound, created a digital analog converter stream, created samples with a digital oscillator, and how we did the conversion with the values. The rest of the course greatly depends upon their understanding to add more features to the synthesizer. In the next lesson, we'll be creating a MIDI serial port interface so we can attach a keyboard to the BP synth and play notes.